Welcome, everybody, and thank you so much for joining us again today. My name is Simon Reuni, and I'm the Global Technical Marketing Manager for YAGEO Group. Today's podcast here again, we have Alexander Nebel, our EMEA Technical Marketing Manager, and he is joining us again for Ask Why Technical Training today. We're going to talk about Inductor Basics and selecting the right inductor for your application. Well, to get started here with the right application, we need to understand the different types of applications that the inductors can actually fall into. Alex, can you help us understanding this a little bit?
Yeah, thank you, Simon, for having me again here today. And I'm happy to talk about some inductor applications. And there are three main applications for an inductor. So the first one is a power inductor. If you have a DC-DC converter, this is one main application for a power inductor. The second one is an RF inductor for any high frequency applications. And the third application is the EMI filter when you want to filter some noise from your application.
I mean, it's great to see these different types of applications, but to go to a very simple question, can you tell us exactly what an inductor actually is?
Well, inductor is very simple. You can consider any piece of wire already as an inductor. But for sure, it's not an ideal inductor. It would be better if you have a coil, a wounded coil, a core, and the core with a relative permeability with a certain material. So this is what we see here on the screen. We have the core, which is marked in orange, and then we have a wound in a coil around it. This is what we consider as an inductor.
All right, I've seen in the field there's a lot of different types of core shapes. Can you tell us a little bit about these core shapes?
Well, the simplest core shape is what we have seen on the picture before, and is also here on the top left, the rod core. But this has maybe some disadvantages. So this is why we also offer different core types. So the toroidal core, which we see on the bottom left, is more ideal because the magnetic field is more concentrated inside the core and is not using the air around it. You can then use also the unshielded drum core, which is seen in the center. And on the top right is the full shielded drum core. And the shielded version is always better because the magnetic field does not have an impact on surrounding items. So depending if there are some items on the next to the inductor, the shielded version is always better than an unshielded version or the rod core.
I mean, you already dived into a little bit of what the benefits are of each of those core shapes, but can you tell us a little bit of how we can easily identify which core goes with which application and where can we use which core shape the best?
Yeah, for sure. So if you take the rod core, the first one, this is ideally for input filters, for example. So what we have seen on the first screen. On the unshielded drum core, this is good for low ripple current applications. And the shielded drum core is for also low currents less than 14 amps with a moderate ripple current. But as I said, where you might have additional products next to the inductor, which might have an impact. The toroidal core, this is something which can be used for high current and also for high ripple current, and when the physical size is not a big issue. And last but not least, the shape core. This can also be used for high currents and high ripple current, also when the physical size is important. So it's more ideal in comparison to the toroidal core.
Well, knowing about the core shape, I know there's a lot more to it. What about the material? Can you tell us about the materials and how I select the right material for my application?
Yeah, the material of the core is very important. So there are different types of material. We can use ferrite material like manganese zinc. We can use metal composite material, flake composite, and also the new nanomet material. And depending on which material you use, you have higher or lower core losses. And for sure, you want to have low core losses. And also you can have higher or lower saturation magnetic flux density. And we want to have a high magnetic flux density. So the nanomet material of the is fitting very good into these requirements, because we want to be at the bottom right of the picture, what we see here. We want to have high core magnetic flux density, and we want to have low core losses, and nanomet would be the best material that can give us all of these.
Well, we talked about the core shape, we talked about the core material, but I know there's one more piece that's missing to actually make an inductor, and that's of course going to be the wire. Now, can you talk about the wire shape and how it actually affects the inductor design?
Yeah, that's right. We talked a lot about the material of the core, but also the wire is important because you can use round wire or flat wire. Round wire is somehow the standard used material, and it gives us a high inductance because I can reach high turns, and this gives me ideally high inductance. But this also means I have a low cross section and I have a higher resistance, which gives me a lower maximum current. But for sure, the cost is very low. But by using a flat wire, which is just the opposite, here I have a very high cross-sectional area and a low resistance, and therefore I can use a flat wire at higher currents. But on the other hand, the construction is more complicated and it needs an additional step, and this is why the cost is slightly higher than the round wire.
Now, when we start looking at inductors in general, a big factor is, of course, going to be the losses. Can you tell us about the inductor losses and how all that comes together?
Yeah, the losses are the most important factor about an inductor. And the total inductor loss is a sum of the copper DC losses, the copper AC losses, and the core losses. And in total, you see all losses here on this slide.
Well, looking at this slide, it kind of makes me dizzy looking at all these equations. Do you have a better way of describing what these losses actually are?
Yeah, for sure. For anyone who doesn't understand all the deep mathematics, we can split the three losses into some easier way of understanding. So the copper losses, this is just the DC resistance of the inductor. So if I have a long wire for high inductance values, or a small cross section, this means I have a higher resistance. And so I want to have a low DC resistance of the conductor, which means I need a bigger cross section or a shorter wire. The copper AC losses, they are mainly the skin effect and the proximity effect. The skin effect is at higher frequency, the current flow will tend to flow on the surface of the conductor. The proximity effect, this means that the current flow is affected also when there is another conductor nearby, which means as soon as I have more than one turn, I will have a proximity effect. And this means I'm not using the full cross section of the copper wire, and this reduces somehow my maximum current, and this will also have an impact on the copper AC losses. The iron losses, this is split into the hysteresis loss, and this is the energy which will be loose and dissipated as heat or acoustic form when AC current is applied. The eddy current loss, this is somehow given by the material. If I have a good insulation, the magnetic field is concentrated into each particle. But if I have a bad insulation, the magnetic field will go through the different particles. So here we want to have a good particle size and a good insulation to have lower eddy current losses. And this is somehow an easy way to describe our three types of losses.
All right, there's a lot of things for me to consider when I'm choosing the inductor. Can you help me summarize this and give it a little bit of an example of how this works?
Yeah, sure. So the easy way and the summary of today's topic are the properties when selecting an inductor. First of all, you always start checking the inductance value and the current. So DC current, but also your peak application current. So with this, you can do a first investigation, which series might fit and which series is out of your range. The next point which needs to be considered is also the topology. Are we talking about a step down, step up converter? What is your input voltage? What is your output voltage? And the most important topic is also the frequency. Some materials are made for high frequency applications and some materials are made for medium frequency applications or low frequency applications. And for sure, we need to talk about the ripple current and the frequency as well. The next point and this is also about the DC losses, is we have to talk about the ambient temperature and also about the maximum temperature of the inductor. So if there is no big delta between the ambient temperature and the maximum temperature of the inductor, then we do not allow high temperature increase self-heating of the inductor. And yeah, for sure, also the mechanical limitations like footprint or height are important. So do you need maybe very flat item because you have limitations in total height, or maybe you have a small PCB and the footprint needs to be very small. And for sure, you might have to consider if you take only SMD or THT products. If there is no other THT item on the board, then you would rather choose the SMD item to not use the wave soldering process. And last but not least, the most important topic most of the time is also the cost target. So is this a cost-sensitive application? Then we might think about using some cheaper products instead of using more expensive products.
Well, Alex, thank you so much for helping us figure out exactly how we can select the right inductor for our application. As you can see, there's actually a lot that goes into picking the right inductor for your application. So if you have questions on that topic, always feel free to reach out to us. We have the experts on staff that can help you pick the right inductor for your application. And with that, I'm really looking forward to seeing you guys again next week for our next topic. And until then, just remember to ask why.
Thank you for having me here today.